Assalamualaikum and good evening. Today I will be presenting about system design, and my part is about introduction. So, in the ever-evolving field of computer system engineering, the demand of reliable and uninterrupted computing services has grown significantly. Two critical design paradigms that ensure system reliability are fault-tolerant systems and high-availability systems. These concepts are essential for the development of robust infrastructures that can maintain functionality during hardware failures, software bugs, and unforeseen disasters. Fault-tolerant systems are designed to detect, isolate, and recover from faults with minimal or no impact on the end-user experience. On the other hand, high availability systems aim to maximize operational uptime by reducing single points of failure and enabling quick recovery. Objectives. This assignment aims to provide a comprehensive understanding of fault tolerance and high availability in computer systems. Explain the key components, strategies, and real-world application of these systems. Illustrate the differences and relationships between fault-tolerant and high-availability designs. And lastly, highlight the importance of these systems in critical computing environments.
Alright, so in this chapter, we will be focusing on 4 topics, which is fault-tolerant systems, high availability, the HA systems, analysis and case study of this topic, and lastly, the findings and the result that we get from the case study. Alright, first of all, fault-tolerant systems. A fault-tolerant system is designed to make the system function even in the presence of a fault. So, this system are built to detect faults, but it will continue operating whether it's in complete normal functioning system, or maybe it will be degrading a bit unless rebooted. So there are 5 key components of the FTES, which is redundancy, error detection and correction, failover mechanisms, replication, and lastly checkpoints and rollback. Moving on to the high availability systems. Okay. High availability systems are focused on ensuring that the services are remain available for as close as 100% of the time as possible. So this kind of application is used during critical systems like ATM or air traffic monitoring system, and also system that use in medical areas such as ECG and so on. Okay, so there are also 5 key components of these systems, which are load balancers, clustering, health checks and monitoring, geographic redundancy, and lastly auto-scaling and self-healing attributes. Alright, to make fault-tolerant system easier to be digest, we provided a diagram of web application mechanism. Right. So the web application, the WW, is the front end that the most users interact with, mostly to open websites or maybe services and so on. So a normal circumstance, the web application will be routed to the load balancer, which then being evenly distributed to the data centers, which contains redundant servers that hosting the same application or even services. So in the event of these data centers fail or maybe having some issues, the web application will be took over by the failover path to make sure the system work as intended, as it should. Even though the normal path is being blocked or failed, the system can be keep working as intended. For the high availability system, which is we put in the context of cloud-based, the normal end users will access the services through the internet, and then being passed to the load balancer, which it receive all incoming traffic and distribute it evenly among the available servers in the cluster. So in high availability cluster, there are two servers, which is the active and the replicated server in standby mode. Okay, so most of the time, these active servers will handle the user request in real time. But when in the event of system fail, the replicated server will be activated and take over the request that being sent to the failed active server.
Okay, now I'll be sharing a few real-world examples of systems that use redundancy and fault tolerance to ensure high availability and reliability. Let's start with aircraft control system. For planes like the Boeing 777 or the Airbus A350, they use something called triple modular redundancy or TMR. This means they have three computing units doing the same jobs, and the system compares their outputs. If one fails, the other two can still keep the aircraft operating safely, which is especially critical during takeoff and landing. Next, we have RAID storage, which stands for Redundant Array of Independent Disks. It's commonly used in server and data centers to make sure that if one hard drive fails, the system can still run without losing any data. Moving on to spacecraft system like NASA Mars Rover Curiosity. This actually has two onboard computers on an A side and a B side. In 2013, the A side and had a memory issue, so NASA simply switched to the B side and the mission continued without any major problems. That's a perfect example of fault tolerance in action. Next is cloud. Okay. In the cloud computer world, service like Amazon Web Service and Google Cloud use built-in redundancy. For example, AWS S3 is designed to be extremely durable with data replicated across multiple locations to prevent data loss. Google Cloud also support live migration and redundant storage, so service and keep running over during system updates or hardware failures. Now for something we all use online banking, platforms like MyBank2You or CIMB clicks are built with high availability architectures to make sure services like payment and transfer are always accessible, even during peak hours or maintenance. Lastly, e-commerce sites like Shopee and Amazon use scalable and redundant systems. During big campaigns, Shopee's infrastructure scales up to handle millions of users at once, and Amazon global redundancy ensures that even if one region fails, the site still runs smoothly for users around the world. So, as you can see, the redundancy and fault tolerance are critical in many industries, from aerospace to cloud service and even online shopping. Okay, that's all.
Now I will be explaining about the findings from the fault tolerance system and high availability system. So let's now explore a comparative analysis table between these two systems, where we look at the key features that differentiate these two approaches. First is objective. The goal of the fault tolerance system is to have zero service interruption, even if a failure occurred. In contrast, a high availability system focuses on minimizing and restoring service quickly after failure. Second, redundancy. A fault tolerance system uses full redundancy, often with active setup or TMR, triple modular redundancy. However, high availability system use partial redundancy, such as active passive pair of N+1 clustering for cost effectiveness. Third, failure recovery. Fault tolerance system recover instantly with no noticeable impact to the user. However, high availability system recover quickly but may introduce short delay during the failover process. In the industry example, fault tolerance is essential in industries like aerospace, space mission, and critical control system, where failure is not an option. And high availability system is more common in areas like banking, cloud service, and e-commerce, where short downtime is tolerable. If you look at the recovery method, fault tolerance system use techniques like voting system or hardware redundancy to mask the failure without destruction, and high availability system rely on failover strategies, traffic rerouting, and replacing fault system to recover quickly. If you are looking at the cost and complexity, fault-tolerant systems are expensive and complex due to the system duplication and advanced logic. And high availability systems are more cost efficient and flexible, making them easier to implement and manage. The example of the implementation for this two system, the fault tolerance is the NASA Curiosity rover, which can switch from the S side to the B side system in case of failure. And for high availability system, a common example is AWS, Amazon S3, which replicate data across different regions to stay online even if one fail. Next, we are going to look at the performance metric between the fault tolerant system and the high availability system using a comparison table. So first is average downtime per year. A fault tolerant system has almost zero downtime thanks to the instant backup that can go immediately. A high availability system may experience 5 to 6 minutes of downtime per year, depending on the SLA, service level agreement. If you are looking at the system availability, fault tolerant system offer a high availability, which is 99.9999%. For high availability system, offer between 99.9% and 99.999%, which is still excellent. Then for the third one is MTTR, mean time to recovery. Fault tolerant system recover almost instantly since they use large backup system. However, high availability system usually recover within 1 to 5 minutes, either automatically or with manual help. Then resource usage. Fault tolerant system keep all the components running at all time, which uses a lot of resource. However, high availability system use resource more efficiently with a mix of auto scaling and standby node. The initial setup for the fault tolerant system is very expensive due to the need for full duplication of the system. But high availability system are moderate to high in cost, but more affordable than the fault tolerant. For the maintain complexity, fault tolerant system high, which is complex to maintain due to the number of active system and synchronization need. However, high availability system medium level, which is easier to manage, even though still require careful monitoring. Thank you.
Hi, my name is Izaz. So let us begin with looking at some observation and trends that have emerged from our study of fault tolerance, which is meaning of FT and high availability for meaning HA systems. Okay, for the first one, we have aerospace, which is the fault tolerance system are heavily used in aerospace and critical systems because they are ensure zero downtime. But this comes with a very high cost. For example, aircraft control system often use a triple modular redundancy to keep the operation safe even if one system fails. In a contrast, high availability systems are widely adopted in enterprise IT environments. These systems are more cost efficient, offer excellent uptime, and are easier to implement for general commercial use. We are also seeing a growing hybrid approach, especially in the cloud infrastructure, with that blending in FT and also HA to provide nearly fault-tolerant reliability using a distributed HA technique, like live migration and also replications. Lastly, there is a strong automation trends that are now designed to detect, predict, and fix an issue without human interventions. So in the conclusion, what we can do to conclude from this analysis, both fault-tolerant and a high availability system are essential to build a resilient and reliable digital service. Fault-tolerant is the best suite for mission-critical system where failure is not an option, like aerospace missions, and then high availability is either for the most commercial applications, such as banking or e-commerce, where rapid recovery or continuous service are the key. And then we go to the trend toward hybrid design that shows the organization are choosing the best both worlds and balancing the reliability, performance, and also the cost. So where are this technology heading in the future? So there is a few steps and a few exciting trends that we should pay attention to. The first one, we have edge computing and IoT. As more devices like sensors and smart machines work at the edge, system must be reliable locally, while still can be connected and available online. Next is AI-driven monitoring. Systems now use artificial intelligence to predict problems before they know what will happen. This will help to avoid breakdowns and keeps everything running smoothly. And the third one is the containerization and orchestrations. Tools, something like Kubernetes, let system to fix themselves and grow automatically without us having a step in all the time. Finally, we have a serverless architecture. This lets apps run only when needed, scale up instantly, and also will recover quickly without needing to manage a server. All these trends are not just making systems more relevant, they are changing the way we build and manage technology completely. And that's all from us. Thank you. Assalamualaikum.